Okay, so welcome to this video where I now do homework 4. Don't know what to say other than, I guess let's get started. So I've got it all open. I already started getting it ready to write the solutions. So let's see. The first problem is, okay, we've got a prime, p, and a natural number k. That is, I guess it's a residue mod p. That's one thing that we can describe it as. And then we want to show that this quotient, I guess it's like a truncated factorial, because it's going to be p minus 1 times p minus 2 all the way down to a certain point, because these cancel it out, is congruent to minus 1 to the k times k factorial modulo p. Okay. So solution. So let's see. Let's suppose p is in the natural numbers, and it's prime, and k in the natural numbers is such that 0 is less than or equal to k is less than p. Yeah, I'm just, being wordy like usual, just introducing what we want to, what our hypotheses are. And I'll just note, like we're just doing this in a straightforward way. Okay, so notice that this quantity is equal to p minus 1, p minus 2, all the way down to, okay, so p minus k minus 1. First of all, let's make sure that makes any sense. So k is strictly less than p, right? So that means that if we do p minus k, we get a number that's at least 1. And if we subtract 1, so we get a number that's at least 0. And so we can take the factorial of that, so that's good. Okay, so p minus k minus 1, that's the one that's being canceled out. I'm going to write, let's calculate in LaTeX. So we're dividing by p minus k minus 1, p minus k minus 2, all the way down to 2 times 1. So the 1 and 2 cancel out, and then we go up to p minus k minus 1, which cancels out, and so the last term that's not oh, there should be a c dots in there. Just, I'll re-render it so I point at the right thing. So the last thing that's going to be left is a p minus k. Okay. So now, let's use congruence. Let's remove that hint. Oh, right. I'm gonna need to be careful here because this version that I'm editing right now, writing the solutions to, are actually the I had to edit them later. So I guess I'll keep this here just in case. So I also gave some additional hints afterwards, and the only problem that really changed was 3a, so we'll just remember that and I'll fix it when we get to it. Okay, so in modulo arithmetic, so recall that for all, let's say I in the integers, p minus I is congruent to minus I, p mod, mod p, since p is not a prox, it's equiv, because p is equivalent to 0, mod p. So hence, this thing is equivalent to -1 minus 2 c dots minus k p mod p. Right. I guess to be really correct about this, we'd want to do, or like really rigorous, we'd prove this by induction on k. Yeah, I probably should do that. Oh, but it's more work. That's not so bad. Yeah, okay. We'll show this by induction on k. So, okay, before I do that, the idea is that, well, we replaced all these terms in the dot 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 too, and we get -1, -2 all the way through minus k. If we pull all the -1s out, we get k of them, and we get a k factorial left over. That's the whole idea. It's not supposed to be challenging, but, you know, it's like maybe discombobulating. Okay. Base case and inductive step. Base case, k equals 0. So when k is 0, how do I want to say this? Okay, we have p minus 1 factorial. P minus k minus 1 factorial is 1. Right? And -1 to the k factorial. So it's 1. So both of these are congruent mod p modulo p since they are equal, because equality is the stronger notion. So inductive step. So suppose, so this is k is greater than or equal to 0, and suppose the conclusion is true for k, we will show that p minus 1 factorial, p minus k minus, k plus 1 minus 1 factorial is equivalent to -1 to the k plus 1 factorial. Okay, so that's what we want to show. And instead of I'm going to just actually state it instead of like using copy-paste technology. Okay. And I can't help making it look nicer. I think this needs to be set off like that. Okay, well, good enough. So that's what we will show. And, okay. We calculate, so at this point, it really is, it doesn't require, I guess, well, it requires knowing where we're going. Like, the stuff that I had written out below that we're gonna, I guess, not really use. But maybe I'll copy some stuff out. So, oops, forgot a slash. Okay, so this is equal to, of course, p minus 1 factorial over p minus 1, or p minus k factorial. But, so let's see where we are. But this is p minus 1 factorial over, maybe I should do a real fraction here, p minus k minus 1 factorial. right? Yeah. Yeah. Let's see. So we got that. Just trying to think of how am I organizing this? Because, okay. I guess I'll turn this into one line. So there are a couple of things I could do. Like, so one thing is, what I want to do is take this, like, pop this p minus k out in front, and then use the result for the second part. Yeah, I'll just do it and we'll see. The problem is, yeah, to do that I need p minus k to be invertible mod p. Which it isn't necessarily, because what if k is... Oh, k is not p. K could be 0, and then that's a p in the denominator. I've already done a basic mistake. So we've got... Yeah, I think I did. That's a minus 2. Oops. Okay, that's good, because that makes life easier. So instead of minus 2, what we can do is recognize the fact that we can take that, and then, let's see, are we able to... I want to say that this is true. Yeah, we believe that, right? Because it's p minus k over 2 factorial. If we cancel off the p minus k minus 1 from the beginning, then we get p minus k minus 2. Of course, there is an issue here. P minus k minus 2 might be negative. So we have to do cases to do this completely rigorously. So if if k equals p, right, well, if k is p minus 1, if how do I say this right? Oh, right. So one of our hypotheses is this, right? But we can assume that for the next case. So then, since p minus k minus 2 is greater than 0, or greater than or equal to 0, we can calculate... Oops, I forgot to close the dollar sign, but it's okay for now. Okay, so we have that assumption. And like, again, I'm just doing this in a rigorous way. Like, this would have been fine as a solution. This is just, you know, a better solution, because, you know, there's no question about what the dot 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 is doing when you do it this way. Okay, so we supposed our hypothesis with the next value, and we supposed the induction step, and that's what we want to show. And since this is true in that case, then we are actually able to do this calculation, which is important. Okay, and then what? Well, mod p, this is equivalent to p minus k minus 1, left-hand side, by the induction hypothesis, right? And then p minus k minus 1 is equivalent to minus k minus 1 and that is equal to minus 1, well, minus 1 to the k. I'll do this in a couple steps. So it's minus k plus 1. Anyway, then we get minus 1 to the k plus 1, k plus 1 factorial. This is what we wanted to show. And then this completes the induction. Okay. Yep, so that's a way to do it. The key thing is what I deleted. Maybe I'll add that back. So this is a less rigorous but more intuitive solution. Which then we can take this and turn it into an align environment so we can do some multi-line reasoning. And then that is equivalent mod, or that's just equal to minus 1. Oop, this is just equal. I like telling the difference between equality and equivalence just for because I think it makes it easier to follow an argument that way. Okay, so that's that. Now the next problem. So for prime p and x and z, then this polynomial is congruent to that polynomial. Okay. So what do we have? We just showed, oh, wait, that's the next problem. Okay. For each prime p and k, then this binomial coefficient, so long as we're not at the top one, top p is congruent to minus 1. So, right. So suppose p is in n is prime and k in n is such that 0 is less than or equal to k is less than p. Recall that the binomial coefficient p minus 1k is a fraction p minus 1 factorial over k factorial p, and then it's p minus 1 minus k, which I'll write p minus k minus 1. It's kind of nice having the constant at the end. So one thing to notice with that is that, except for the k factorial, that is what we studied in the previous problem. So the thing that we want to do is justify why we can divide both sides by k factorial. Right, yeah. So one thing is, notice that we have that the GCD k factorial and p equals 1, since every divisor of k factorial is, it is since k is less than p, and this was a result from lecture, that factorials have this property, and p is prime. Because if the GCD were not 1, it would be p, and then p would divide k factorial, and then by the primality property, it would be p divides 1, or p divides 2, or p divides 3, all the way up to, or p divides k. But k is less than p, so none of those happen. So the GCD is not p, and that's 1. Thus, k factorial has a multiplicative inverse modulo p. Multiplying both sides of the congruence from part A by this inverse, which we don't need to calculate it, we just need to know that it exists. We get what do we get? Let's just copy it. So I'm going to write it as a fraction. So we're setting it off like this, and then k factorial to the minus 1, that's the inverse. K factorial to the minus 1. Okay, now, by definition of multiplicative inverse, k factorial to the minus 1 k factorial is congruent to 1. And since k factorial divides this, then we can just divide. Okay, so then, simplifying that, we get k factorial on the bottom, and then the k factorial and k factorial inverse cancel out, and then that's what we wanted to show. Yeah, so that's one way we can argue this. Okay, well, it's done. Okay, I just want to see how these compare so far. Yep, okay. Okay, so the next problem. We got that, I've already set it when I got lost with where we were. And it hints to use the binomial theorem. So again, suppose p is in n is prime and x is in z, then by the binomial theorem, we have a line minus 1, or 1 minus x to the p minus 1 is equal to the sum for There's two ways to write sums. I like doing it where there's just I guess an inequality instead of, I'll show you both of them. So one option is sum from 0 to p minus 1 of binomial coefficient of p minus 1 I. Then what? x1 to the I plus minus x to the well, p minus I minus 1. I think it's fair to just, this is like the bad variable. It would have been better to I'm gonna do it as minus x plus 1, just so there's the parallelism. Like, I just want to index it so it's actually I on top of x. Just better. It doesn't really matter. But that's, yeah, so that's taste. And this immediately simplifies. Okay, so that's one way to write the binomial theorem. Ooh, wait, what am I doing? That should be a times. Okay. The other way to do this is 0 is less than or equal to I is less than p. I just think it looks nicer, makes the inequality clear. So it's the sum over all things that satisfy that property. Okay, so then equivalent mod p, this is to, we can replace that with minus 1 to the I. I guess I could have used k, but because then it would match up with the problem, but hey, this is fine. So then, well, okay, first let's simplify it. Like, that 1 is not doing anything. And then that's equivalent. And then that is equal, so the minus 1's cancel out, right? And then we can just use our dot 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 notation to write it as, so x to the 0 is 1, x to the 1 is x to the 2 is x squared, all the way up to x to the p minus 1. This is what we wanted to show. Or let's say, which is what we wanted to show. Yeah, so it just turns out there's that one step in there that is an actual congruence, and the rest are equalities. Okay. Now what? So we've got this polynomial, and now we want to show that we can simplify it if and only if x is neither 0 nor 1 mod p. Okay, so suppose p is in n and x is in z. Now what we want to do is decide how we're going to prove this if. So one thing is, the difference between these, like the x to the p minus 1 is missing. So it's probable that this is a Fermat's little theorem problem. And similar with that p minus 1 power disappears. So for the forward direction, we probably just do it like normal. And so for the backward direction of this if, so we'd assume that this is true, then we want to show that neither of those are true. It seems easier to show the contrapositive. That's assuming that this is false than showing that that's false. So I'll say to show the logical equivalence we will show I guess let's see, how do we say this normally? So we'll show that if that, then that. Let's remove a couple terms because I think we get the idea. Along with its contrapositive, that if, let's just copy it, modify it. Okay, so the logical negation of and, of course, is not or not, using De Morgan's law. So, and also we need to negate the conclusion. Okay, so suppose P is prime and X is in Z. To show the logical equivalence, we will prove that if X is neither 0 nor 1, then we get this congruence. And let's turn that into a sub P just for compactness. Along with its contrapositive, which is compactness, which is that if X is 0 or 1, then it's not equal. So that's what we're going to do. So first, assume or suppose these two hypotheses. Okay, by Fermat's little theorem, since X is not 0, we get X to the P minus 1 is equivalent mod P to 1, and also, well, I'll say this, the second this second hypothesis implies that 1 minus X is not equivalent mod P to 0. So that's the key for that, because then we can say that 1 minus X to the P minus 1 is equivalent mod P to 1. Hence, by problem C, we have that 1 is equivalent mod P to 1 plus X squared plus dots plus X to the P minus 2 plus 1. I'll write P mod. Subtracting 1 from both sides, we get that, well, we get what we want, which is that 0 is equivalent to that polynomial, which is what we wanted to show. Second, okay, let's see how this is going. I still haven't gotten around to getting, like, this is just like a one-line configuration in LaTeX somewhere, but I just haven't gotten around to it. Maybe I'll do it next week to get that little gap for the paragraphs. Okay, so second, suppose that one of them is 0. And let's do it by cases. So case 1, case 2, x is equivalent mod p to 0, x is equivalent mod p to 1. We see that 1 plus x plus dots plus x to the p minus 2 is congruent mod p, well, it's equal to 1, which is not congruent to 0 modulo p, since p is greater than or equal to 2, because it's prime. And then, in there is that 1 and 0 are both residues, so mod 2, like, they're already reduced, so they're not equal, so that's all we had to check. Case 2. We see that 1 plus x plus c dots plus x to the p minus 2 is 1 plus 1 plus c dots plus 1, which is p minus 1. And since 0 is less than or equal to p minus 1 is less than p, again, for the p is greater than or equal to 2, well, let's see. Well, then, since p is greater than or equal to 2, so that means that p minus 1 is well, this is true. Then p minus 1 is not congruent mod p to 0. Okay, in both cases we showed that the conclusion holds, which is right up here. Hence we have proved the converse. Oh, no, contrapositive. That's... No, wait, why am I calling this the contrapositive? The contrapositive is the... I just forgot what this one's called. I think it's called the inverse. Yeah, okay. Inverse. So the converse is when you flip it, the inverse is when you take logical negations, and the contrapositive is the inverse of the converse. And to prove a logical implication, you just have to show either the forward direction, the statement and the converse, or the statement and the inverse. And so we chose to do the statement and the inverse, which is the contrapositive. I'll just... the contrapositive of the converse. Okay. So that's the idea. It's just plugging them in and seeing that it does not actually give you the value of 0. Okay, next problem. So suppose p is prime and p is 3 mod 4. We'll show that minus 1 has no square roots modulo p. So minus 1 is not a quadratic residue modulo p, using some other terminology. or there's no number that squares to a number that's congruent to -1. Okay, let's compare this to the other version of the homework, the actual version. Okay, and this problem just got some more hints. Okay. Okay, so for all x and n and m, if both of these are numbers, if these are both exponents for which we get 1 modulo p, then we could have instead taken it to the GCD. A way I think about this is, so like x to the n is saying that if we keep multiplying by x, we go in a circle and get to the beginning. And m is saying that if we go along another circle, we'll get to the beginning. And so if you kind of like do both circles simultaneously, well, I guess the smaller one would be faster. So like as we're doing both of these circles some number of times, then I guess if you kind of like wrap them, well, the GCD ends up being the radius of the circle, or the circumference of the circle that both of them wrap onto an integer number of times. Not sure if that helped, but okay, so suppose x is in z, n and m are in the natural numbers. X to the n is congruent to 1, and x to the m is congruent to 1. Well, what can we do? Let's do Bayes' identity. That seems to be the solution, always. So let a and b in the integers be such that x to the a n plus bm equals 1. Oh, no, not 1. The GCD. Okay. Now we're now at the point where we don't even need to mention Bayes, but because it's just what you do. But which exists by Bayes' identity. Yeah, I'm using a LaTeX instead of ZTeX or LuaTeX. Just good old PDF LaTeX, and it does not have Unicode support. So if I did like, so I'm just able to type that with some compose key. What will happen? No, I actually did the right thing here, but that is something I cannot count on. Okay, so that's what these codes are for. These ancient codes for installing accents. So we have, and maybe this is using some rule that we've never proved, but I did mention that we could prove it in lecture. So maybe that's good enough. We have that x to the nm is equal to x to the an plus bm, which is equal. Okay, so yeah, here's an issue. A might be negative, B might be negative. So I'm just going to turn this into a congruence. Because, you know, they might be negative, so we might be calculating inverses. And so let's see. Let's use our exponentiation laws. And then, yeah, which we didn't prove. But maybe I'll prove them here. In just a moment. So let's see where we are. So we used Bayes' identity, used exponentiation laws, and then by hypothesis, x to the 1, or x to the n is 1, and x to the m is 1, and that is 1, which is what we wanted to show. So we use some exponentiation laws. Exponentiation laws involving negative exponents. So, which means and actually, like, almost surely one of the two is going to be negative. Which means that so in lecture we said meant to take the positive exponent of a multiplicative inverse, which is that like x to the a is equivalent mod p to x to the minus 1 to the a, to the minus a. So let's check one of them. So if x is congruent to y, then x inverse is equivalent to y inverse. So what we need to see is, well, y inverse x is equivalent to x inverse x by a multiplication law, which is equivalent to 1 by the inverse law, the definition. Oh, wait, what am I showing? What I mean to say... Oh, wait, is this something I proved in lecture? I think I actually proved that one in lecture. Just, let's see, where would that be? All the files. When was that? I think, yeah, it was the Fermat lecture. Where's the PDF? Huh. So let's see. I did show that, right? Because I remember saying, like, it's one of those nice little facts that oh, okay. Yeah, okay, if we got two multiplicative inverses, then they're equivalent. Oh, okay, I only said that two multiplicative inverses are the same. So by the uniqueness property, y inverse is equivalent to x inverse. So that's the thing that was proved in lecture uniqueness, and so we can, because when we, why did I delete that x? Since it acts like an inverse, it's an equivalent one. Okay. All the other things, it really is a very similar sort of exercise to show. Okay, now let's prove that 4 and p minus 1 have a GCD of 2. So I'm going to use the Euclidean algorithm. So notice that p equivalent to mod 4 to 3 means that p after division by 4 equals 3. So, well, from this, we get that p minus 1 is equivalent mod 4 to 2. So p minus 1 remainder, after dividing by 4, we get remainder 2. Hence, 4p minus 1 is 4p minus 1 remainder, or divided mod 4, which is equal to 4, 2, which is 2, because 2 is the GCD of 2 and 4. That's it. Okay, now C. For all x, if x squared is minus 1 and x squared is 1, which seems a little weird, but part D is, we're trying to do a contradiction proof, and I wrote this to help you see how to do that. And so if they are the, like we want to, so we want to conclude that. And this is a little non-trivial, so the hint is to use 4 and, oh, that should have been an m. 4 and p minus 1. So suppose x is in z and x squared is equivalent mod p to minus 1. Then, by the oh yeah, I never mentioned that x is, okay, we have that x is not equivalent mod p to 0, since if it were, x squared is equivalent to p, it's equivalent to 0, but minus 1 is not equivalent to 0 mod p, since p is greater than or equal to 2. Well, it's actually greater than or equal to 1, but no, yeah, p is not greater than or equal to 2. Hence, by Fermat's last theorem, little theorem, we have x to the p minus 1 is equivalent mod p to 1. Since x squared is equivalent, we also have x squared, x to the 4 is equivalent mod p to x squared squared, which is, well, that's just equal. That's an exponentiation law. That's equivalent to minus 1 squared, which is 1. Thus, we may apply part A to conclude, to get that x to the GCD of 4 and p minus 1 is equivalent mod p to 1. By part B, this is that x to the 2 is equivalent mod p to 1, which is what we wanted to show. So it's kind of a bit of plumbing in this problem. Just taking some of the things, setting it up to use the previous two results, and then we get this seemingly absurd thing. So the last thing is we want to show that if we have an x, when we square it, it's not minus 1. Because if it were, well, then it isn't. Okay. So, yeah, and then this is what it means for there to not be a square root. This thing has no solutions. So suppose x is in z. Assume, for sake of contradiction, that x squared is equivalent mod p to minus 1. So assume the opposite of the conclusion. Then by c, x squared is equivalent mod p to 1, which implies that minus 1 is equivalent to 1. Are there a few things we could say here? Well, like, that just can't happen. I'm just trying to decide what of the many ways of saying that this is impossible do I want to use. Any of them work. So let's say by definition of congruence, this means p, like it's going to be 1 minus negative 1 that p divides. So since p is prime, p equals 2. But that's where the contradiction happens. But p, but 2 is not equivalent, or it's not congruent mod 4 to 3. Contradicting that p is congruent mod 4 to 3. There we go. That's the second problem. Okay, now for this next problem, I need to homework for V2. I'm just gonna copy out this whole thing. That way I don't have to refer to it. Okay, let's replace. Okay, so when it's 3 mod 4, there's no square root. And when it's 1 mod 4, it has a square root. And we're going to use Wilson's theorem or something for this. So first part, and this is very similar to what we did up here, or these sorts of things. We're going to show that if p is odd, then we can rewrite p minus 1 factorial in this form. And we'll see why that works. Okay. So the question is, do I want to... I'm not going to do induction for this one. We could do it, but I think it just obscures the reason here. Also, kind of want to, get this done. But, do I do induction and do it right? This is the part where I try to talk myself into giving you the more complete, rigorous solution. Induction is a little annoying. I don't think it's very, let's see, perspicuous, I think is the word. So let's do this with dot dot dots. Okay, so suppose k in the natural numbers is such that p equals 2k plus 1. Which exists since p is equivalent mod 2 to 1, because well, 2 divides 4 and we can reduce the modulus that way. Okay, we have, by Wilson's theorem, we have that p minus 1 factorial is congruent to minus 1 mod p. Then let's notice that p minus 1 factorial is equal to 1 times 2 times and so on up to k minus 1, k plus 1, k plus 2, how many do I want? Yeah, dots p minus 2, p minus 1. Let's see how that looks so far. So I've written out a bunch of terms. And then, so k is what happens when you divide p minus 1 by 2. So, okay, so what I want to do let's add, so since k plus 1 is equal to, just trying to work out, it should be p minus 1, or it should be p minus k. Because, yeah, look, if I add k to both sides, then I get this equation. So we can take this and turn that into p minus k minus 1, and so on. Oh yeah, this big gap, by the way, it's from this additional break at the end. It's just we're going to use it, but it's something I usually look for. So then, this is equivalent mod p to this. And then, you know, for the same reason as before, p is 0 mod p. And then, by rearranging, we get 1 minus 1, 2 minus 2. All the way up to k minus k, which is minus 1 to the k, 1 squared, 2 squared, all the way up to k squared. Hence, oh, we have what we want. I wonder if I should put well, I guess if you can, Hopefully that's clear enough. Also, I think I wanted the k minus 1 in there. Yeah, I was just trying to decide. Yeah, okay. I think that's fine enough. So do you see why induction would be a bit of a nuisance? It's because there's this breakpoint where we decide that we're going to rewrite it as p minus k. And as k increases, then that breakpoint has to move over and we have to like configure that. And it's not bad, it's just this is clearer than whatever that induction proof would be. And like, you know, somebody who's well acquainted with induction would know how to write that. And that's why this counts as a proof. Because, you know, if you just keep asking them why, then they'll make the proof more and more rigorous. So if you write something like this, be sure you can do that. So this next problem, it's actually just what we did already, just, well, yeah, it's like, it is what we, so notice, okay, so suppose that k is in the natural numbers and p equals 2k plus 1. Notice that k factorial squared is 1 squared, 2 squared, all the way up to k squared. If we multiply both sides of the congruence from part A by minus 1 to the k, then we get that k factorial squared is congruent mod p to minus 1 to the k plus 1, which is what we wanted to show. Great. Now, this is just this should be an easy observation. If k is this quotient again by 2, then k is even. That's what we want to show. So, how do we do this? So by since p, okay, so let's take our numbers like usual. Since p is equivalent mod 4 to 0, 1, then we have that 2k plus 1 is equivalent mod 4 to 1. So by subtracting 1 from both sides, 2k is equivalent mod 4 to 0. Since 2, 4, the GCD of them divides 0, because everything divides 0, it doesn't really matter, then we can divide everything, including the modulus, by 2, 4, which is 2, to get an equivalent congruence. Namely, k is equivalent mod 2 to 0, which is what we wanted to show. So that's one way to prove it. Another thing we could do is just try plugging in k equals, we'll see what happens when k is even, see what happens when k is odd. I'll show that too. Why not? Okay. We will show that k is equivalent to, okay. Let q and r in the integers be such that k, let's copy this just for completeness. Okay, k is 2q plus r, and 0 is less than or equal to r is less than 2. So division algorithm. Then p is equal to 4, let's see, I'm plugging k in, 4q plus 2r plus 1 and that's equivalent mod 4 to 2r plus 1. Since p is equivalent mod 4 to 1, then this means 2r is equivalent mod 4 to 0. And we can check that out of r equals 0 and r equals 1, only r equals 0 solves this. Therefore, k equals 2q, so k is equivalent mod 2 to 0. That's another way we can argue that. The world is your oyster. Okay, part D. K factorial squared is a... oh, I forgot to actually mention what k was. I think you probably figured it out from context. But let's correct it here. And I'll put this conclusion here, because that's, we don't need to prove that, but that, you know, that's just what k is. K equals p minus 1 over 2. Okay, so lost track of what we're doing. So, oh right. So, let's add that like usual. Okay, by B, we have k factorial squared is equivalent to minus 1 k plus 1 which is minus 1 to the k. We'll negative that. By C, k is even, so minus 1 to the k is 1. Hence, k factorial squared is equivalent mod p to minus 1, which is what we wanted to show. Okay, so that's that. I'll post these later, and I'll see you in class. I'll see you next week with more homework. Goodbye.